It's a pleasure to be giving this lecture and telling you something about mainly what I do and the implications, and also to do it being dressed up, which is completely unusual for an experimentalist. I'm going to be talking about the constituents, going elementary in that sense, but I want to give you the warning that what we consider elementary and what we consider as primary constituents may change in the future. And so we're going to discuss with the approximations we're using to describe nature, and we are going to always scrutinize on what is beyond that. So I will start with the standard model, and I will call it the standard theory because it's really truly a remarkable theory that deserves the applause of the measurement of quantum mechanic measurement that Brian showed you, together with the prediction. The standard theory or the standard model of particle physics or the standard model of particles and their interactions, namely the forces, has been verified across many length scales, 24 in particular, to 1 per mil with more than 100 measurements. This does not happen in any other field of science. There's no such a theory in any other field of science that covers so many phenomena over so many energy and length scales. So we need to keep this in mind, and this is why I like it to call it the standard theory. It's very much a very beautiful theory, and standard it means that it works. It doesn't mean that it is in any way, form, or shape trivial. So the quantum field theory is the standard framework that we're talking about particles and all the interactions and whatever we are going to be talking about in terms of collider physics. We're talking in graphs. The easiest way is we're talking in graphs. We have also other frameworks that have a lot of algebra and matrices and so on. But the easiest way was in graphs, and because it was the easiest and the most intuitive way of describing the interactions of the particles, we made it a stamp so that everybody can feel comfortable looking at these graphs. The graphs have on the right side, you see a graph that has lines, wiggles, squiggles, arrows, and usually a convention is that such a graph is describing an interaction from the particles in the left as initial states to the particles on the right as final states through an exchange of a particle in the middle, which in this case is the photon, is the particle that mediates electromagnetism. And so you've got there E plus, E minus, annihilation. It goes to a photon, and the photon gives you quark and anti-quark pair, two pairs of particles. In the meantime, on the outside line, you've got the squiggly thing, which is a gluon. So a gluon, the mediator of the strong force, is being emitted. If I want to take this diagram, and one graduate student that has learned how to write down the mathematical expression for how this diagram can be mathematically calculate the strength of this reaction, then I can actually assign for every vertex, for every line, and for every squiggle, I can assign a term, and then I'm talking about, I can talk about this reaction in math and figure out rates for this reaction to be happening. So this is the language that we are talking about, and you will hear more on this throughout the day. So now it gets hairy with this language when you try to make it math. The standard model or the standard theory is giving you the blueprint of the universe, and in here, the thing that I want you to notice is that it looks to a Greek, it looks like Chinese. Somebody who knows the math and the physics can actually read this, and you can read in this light, you can read interactions, you can see the Higgs field, but all of you can see that there is not a single mass term in there. There is nothing that says mass of electron, mass of Higgs, mass of anything. All right, so this is the theory that we have for particles before they acquire mass. In its normal state, the standard theory particles did not have naturally mass, which is in violent disagreement with all our, when we weigh ourselves, with all our weights. So we're going to come back to this representation a little bit, because this is before the dynamics of the theory is giving me the mass through the Higgs that you all have heard. You're going to hear also this, about this representation of the particles throughout the day. We've got on the top block quarks, and on the bottom block leptons. And we've got one column there, the photon, the gluon, the Z boson, and the W plus and minus 2 of them bosons. And all of these are mediators of the forces of nature. Well, is there anything impressive here? This looks like categorization. It looks like we're taking specimen and we're making categorization. And indeed it is. We have the categorization is made according to the symmetries that these particles are interacting according with, and all their quantum mechanical properties, including also the mass, okay, of each one of these. There is some patterns there on the mass, but we cannot say much about these patterns, where they come from. It's an open-ended question. Now, the one thing that will be recurring in what we're talking about is spin. And for the leptons on the bottom and the quarks on the top, the two blocks up and down there, the spin is a half. And for the column on the right, the spins are the spin of the W and the Z and the gluon and the photon is 1. And I'm not including in this picture anything about gravity. Unlike Brian, I'm very scared of gravity. So when I mention it, you will know that it will bring all dark problems. So, but let me show you in a pure Feynman way what is the difference between spin, because spin is associated with spinning. You all know ballet, and spinning is spinning. So if I spin and I do a full spin, I will see the world the way I left it. I will see the same world that I left. The fermion, however, that has a half spin, it looks like a system that it is my hand together with a bottle. So if I turn it in space, a full 360, I got a problem. It acquired a phase. I have to turn it another 360 in order to be where I started from. That's the difference of the fermions with the bosons. Although another thing to remember is that if we had a theory, if we needed to build theory of the world and the world was only bosons, it would be a very easy world. Fermions are the difficult, really difficult part of understanding the universe. Okay, so there they are, fermions, spin a half, bosons, spin 1. And all of these bosons were force carriers. And now I'm putting them in a little different way, so I'm categorizing them according to their masses. On the top, the leptons, we've got neutrinos, and we've got the leptons, electron, muon, and tau. And on the bottom quarks, I've got up, down, charm, strange, top, bottom. And the top, I had to take it out a little bit because it's huge. In fact, when I went to school, the top had less mass than the W boson, and so the W was decaying to a top and a bottom. And then during the time that I was at school, the top was discovered to be 170 GeV and decayed to a W and a B. Now, and here are the bosons. There is the W, the Z, the photon, which mediate electroweak force altogether, or the photon alone electromagnetism, the W and the Z, the weak nuclear force, and then the gluons are mediating the strong nuclear force. And we're going to see them a little bit in a moment right now. How exactly, which are the phenomena? For the photons, you know the phenomena. There is electromagnetism, and you know physical phenomena that occur in the everyday life that involve these reactions. In the description that we have in the blueprint that I show you, which didn't have masses, when we put the masses, by whichever mechanism, we will see it's the Higgs, the terms that are showing up there as electromagnetism are shown up there. There is electrons and U quarks and D quarks and the A mu there. This is the mathematical way of describing this phenomena. For the weak interactions, the phenomena that we see from the thermonuclear reactions in the sun, all the neutrinos that we get, for example, are based on the reactions of the W changing the flavor of one quark to another quark. When I'm speaking in those terms, I want you to remember that when I'm talking about decays of a particle to 2 particles or a particle to 3 particles, it does not mean that a particle contains those particles. It means this is a quantum mechanical process. And so there is a transmutation, if you want, of one quantum mechanical state into other quantum mechanical states. Now, the gluons mediate the strong force responsible for holding the quarks together into the protons, for example, and in fact, we know that the lifetime of the proton is as big as the lifetime of the universe, so this is one of the experimental constraints when we build theories. Now, the full standard model was written in 1967, before the Higgs mechanism or the Higgs particle or the Higgs field was discovered, but the Higgs field was theorized. The Higgs field is very difficult to discover. You have to excite it and make particles, and this is why it took so long time in order to create particles. And this is now the blueprint became from the top, which we saw on the previous page, into the bottom. Okay, so a lot of people say that the standard model is very beautiful and simple. So this is the amount of simplicity we're talking about here. But now I want you to look here and start identifying terms with masses. A mass, another mass, the mass of the Higgs, and some masses squared. So what happened in the way we went from the top equation to the bottom equation is that we call it symmetry breaking. In fact, we call it spontaneous symmetry breaking. So some dynamics happened, and the particles acquired mass. And the dynamics is happening via the Higgs field. Again, if I take all these lines, I can find now, again, light, the electromagnetism, I can find the weak force, and then this balance there is what I pointed out, we have all the mass terms. So the simple picture is the quarks, the leptons, and the forces through the gauge mediators there, the W, the Z, the photon, and the gluon. And behind all that is actually the Higgs, which we have been looking for 40 years. And is there anyone in this class who doesn't know that the Higgs was discovered recently? No. So the Higgs became a superstar. The Higgs, the particle, the people who found it, etc. It became a part of our everyday life because it is extremely important. And because without it, we were not, this beautiful standard model with all these confirmation that we had was sitting in a place, in a very peculiar place without understanding the source of mass. So now we got it. In 1967, it was put into the theory of leptons and quarks, and into the theory of leptons first, and we had the electroweak standard model, and then the theory of quarks, quantum chromodynamics came along, and we have the full theory of quarks and leptons and forces, which is called the standard theory. Now, in order to arrive to this point experimentally, the program of the past century included the cosmic rays, because a century ago, we didn't have accelerators yet. However, the accelerators, big accelerators exist in the universe, supernova. We have protons that are arriving in our atmosphere. They interact with the molecules and the atoms in the atmosphere, and they create subatomic particles like pions and muons, all the subatomic particles that then we discovered in colliders. It is the accelerators, there is a great number of accelerators that is shown here. Usually, the accelerators are based exactly on the fact that you can exactly on the fact, like as a battery, you can give impetus to a subatomic particle, usually electrons or protons. Protons are taken if you strip the electron of a hydrogen atom. And then you circulate them, you put magnets around their path, and you pump a lot of energy in them and bringing it into collisions, either head-on collisions between two colliding beams. This was the big advance of the 20th century that gave us many discoveries, like the top quark, for example, or in fixed target experiments, which was previously the case. You see that the accelerator started in the middle with an 11-inch cyclotron, so at Berkeley. And now, as you know, the LHC is 27 kilometers in the circumference. So we have gone from very small tabletop accelerators into the Godzilla accelerators. And of course, when you go through this process, you realize at some point that materials are your issues, and you have to start again shrinking your accelerators. So you have to find new techniques to accelerate particles. And this is on the forefront right now of accelerator technologies, to figure out a way to make an LHC on my table, at least, not your table, but my table, my lab. And then we are going to have some more progress with regards to how we go into higher and higher energies. Okay, so let me tell you my trajectory through these accelerators. I went, first I started as an undergraduate, I did some work in a synchrotron lab in Germany, and then doing material science using the photons from, using the light from a synchrotron source. It was, again, a synchrotron machine, an accelerator. And then I went to CERN, again as an undergraduate, and I was completely fascinated with the fact that I could build an experiment. It was a prototype, but I could build it on my own. I could calibrate it. I could do the data acquisition. So I can hands-on put together an experiment myself, which was then used for purposes of a bigger experiment. At that time, it was Delphi. Which was a large electron-positron collider in Geneva on the same tunnel that the LHC is. So I went from the Tevatron, and there are some pictures there from the Tevatron with the shorter hair and younger face, all the way to the LHC, 20 years, so 10 years at the Tevatron and 11 years at the LHC. It's a long path for these type of experiments to yield results. And as an experimentalist, the work that we do is to build the detectors, to test the detectors, to take data, analyze data, and make sure we produce results, of course, like the Higgs. Now, from the full standard model, the thing to remember is that naturally the particles do not have mass. They can acquire mass through dynamics. And for gauge bosons, the Higgs mechanism is exactly how it works. So the little sombrero that we saw, which represents the symmetry breaking mechanism, is how the W and the Z acquire mass. The other particles, the quarks and the leptons, they also acquire mass through interactions with the Higgs. And on these, we have a lot of work to do in order to measure the Higgs decaying directly to the fermions. For the bosons, what we have found is enough to tell us that this Higgs that we found is indeed the symmetry breaking mechanism that gives mass to the W and the Z. For the mass generation for all these different flavors, why, for example, the strength of the coupling of the Higgs to the electron is smaller than that to the mu and is smaller than that to the tau, which gives you the hierarchy of the masses of the particles and the patterns that we had there previously, we have really no clue. It's a big mystery. All right, so now I want to wrap our minds one moment again on quantum, on the quantum. When we talk about particles, we talk about particles as states that are interacting through a particular kind of a symmetry and force. In addition, we have what we call the mass eigenstates, in other words, the physical realization. And in nature, it is allowed, and specifically for the quarks and for the leptons, we will see, that they mix. So there is a little bit of each of the flavor in one mass realization. And they are not pure in that sense. And how much they mix is important because behind the mixing of the particles, one might explore a big question about the universe, namely why the universe is mostly matter and not antimatter. The universe we live in, all of us, we are matter and everything on the universe. The universe is dominated by matter and not antimatter. So in this representation here, there is a matrix that you see all the elements are talking about the strength by which a quark goes to another quark. And they're called, it's called Kabiba-Kobayashi-Maskawa matrix. And I'm not going to repeat it throughout what we are talking today, but in every slide there is usually a Nobel Prize or two of what I'm showing. And on the bottom here, I've got again all the quarks that we talked before in the same sense, UD, CS, TB, and then strong, weak, the way each one decays can transition to another one. And so we have a program of 50 years of understanding the quark sector of the Standard Model, understanding how they mix, and measuring the mixing angles and what we call the CP violating phase. CP stands for charge and parity. Charge is the symmetry between matter and antimatter. If you change charge, you go from matter to antimatter. Parity is looking at the phenomenon in the mirror. And so together, if you combine these two symmetries, you get charge parity symmetry, which when you violate, you can start understanding, for example, the matter-antimatter asymmetry. And we see that it happens in the quarks. These are the measurements of the elements that I showed you before. So you can start observing and doing a little bit of numerology here. The elements on the diagonal are the strongest. They are 1. The elements off diagonal, they have some sort of asymmetry. One is smaller and the other is very, very small, the very diagonal ones, the 0.03 and 0.008. And this is giving us insights on the structure again of the mass eigenstates and the gauge eigenstates, as we call them. The program has taken us for 50 years with experiments in Japan on the top. It's called BEL. Experiments at SLAC, which have now finished in the past 5 years. They stopped in the past 5 years, which is called BABAR. BABAR stands for B bar. B bar is the antiparticle of the B quark. And what we were trying to find is this type of oscillations and mixing in B mesons, which are comprised of B quarks also. And right now, the LHCb at CERN. Now, when we go to leptons, the situation becomes hairier in the sense that we've got, well, whatever we predicted in theory for the part of the leptons that are neutrinos was wrong. And we thought that the neutrinos would be massless, but the neutrinos, we measured them to have mass because they oscillate, because the same quantum phenomenon happens. And everything that we expected about the strength of the oscillation and the way they mix was pretty much off. To give you an example, this θ13, which is one of the mixing angles, we see there that it's 9.6 degrees, and before the experiment measured that, it was thought to be 10 to the minus 10 or so. So it was thought to be very, very small. Now, we have not measured this phase that is related to CP violation, and this is part of a program that is being initiated so that with an international program, but based in the United States. I can answer questions about that. So now, if we write the same kind of mixing matrix for the leptons, we see that the numbers are all over the place, and they have not, and very different from the quark one. So, and we don't understand this yet. And I want to say that indeed, for 50 years, this is another program of 50 years that started with Ray Davis at Homestake mine, and everybody thought he was crazy. He measured that the solar flux, the neutrino flux from the sun had a deficit compared to the solar model. And then Super Kamiokande in Japan and Snow in Canada, they verified, in fact, that we do have oscillations of neutrinos, and that neutrinos have tiny masses. Now, so close, so far away. This is what I think to take home here is that there is an analogy. The quantum world between leptons and quarks is working in some analogy, in that those nu e, nu mu, nu tau are the three neutrinos. These are the gauge eigenstates, and 1, 2, 3 is the physical manifestation of them. And you see that they are comprised, each one, 1, 2, 3, a little bit of each. This is, again, the quantum mechanical, the quantum mixing of the gauge eigenstates. And the same thing is happening, as we said, in the quark sector, but you see it's the magnitude of it is very, very different of the mixing of the states. All right, so now the flavor questions are what are the dynamical origins of the fermion masses, their mixings and CP violation? What are the energy scales that are associated with the dynamics, and also which are the symmetries and symmetry breakings associated with that? As I speak like that, since I explained to you something about the Higgs being the symmetry breaking mechanism that gives masses to the W's, the Z's, you might already suspect that we might have more Higgses, an extended Higgs sector that will start giving us answer for this type of problems. In addition, we're going to see that in order to patch some issues that we have with the theory and the Higgs at the mass that we found it, we might need supersymmetry, and supersymmetry is giving us also additional particles that have to do with dark matter. So we have to establish the connections among all of these. When we are doing the analysis of the data, it is always, we are not just trying to verify the theory, we are always trying to see the data for what they are, okay? We're not always including the theory before we analyze the data. Of course, when we have many theories, we can analyze the data into many ways, and this is where the standard model won in all these cases. Okay, so let's move to the LHC and the Higgs. Now, the Higgs is the boson that was missing in the table that we had before, but it is not the same kind of boson like the other bosons we talked about. We talked about bosons with spin 1. This one has a spin 0. We have not discovered a particle with spin 0 elementary ever. This is the first one. And we think it's elementary, but we're still working to figure out whether it's yes or no. Now, in these words that I have up there, I call the Higgs also a new force of nature, and the nomenclature is a little bit mixed up because the forces we note as the ones that are carried by gauge bosons, which are the W's, the Z's, and the photons, and not by and the gluon, and not by a spin 0 boson. But for all practical purposes, you can change a little bit the nomenclature and call the Higgs a force, a new fundamental force. Let me show you a little bit how an aerial of going down to the LHC, 27 kilometers around, in between Switzerland and France. My office is somewhere there at CERN, close to the airport, and now we're going to go underground, about 100 meters underground, both experiments. This is the Atlas experiment, which is in Switzerland. And this experiment was built in situ there, and what we're looking is a time lapse of 4 years where the experiment was built, a part of the detector was built. What we're looking inside is the calorimeter, and this arachnoid structure around is nothing but a toroidal magnet. The magnet is used in order to bend the particles, because when you bend the particles, you can figure out their momenta, and this is why you have the magnets. And this is the tunnel. There's about 1,300 of these dipoles, 14 meters each. The dipole technology is pretty amazing. Within the same magnet, you have beams of protons and protons going the other way in order to collide within the same magnetic field. This is highly non-trivial. This was discovered by John Blewett at Brookhaven Laboratory in 1970, and it was not picked as a technology for the SSE. The SSE was 2 tunnels with 2 different beam pipes. This one is 1 beam pipe, which is only splitting at the experiments. And it's an amazing technology to actually build this type of magnets that will do this. Now, what we saw in the movie was also another kind of pipe you saw there, and this is the pipe of the liquid helium. I said that the magnets are superconducting magnets, and they produce the field needed for the protons to remain around the ring and be brought to the very high energies. And the superconducting magnets, they need about 9 tons of helium in order to be operating. This is the biggest density of helium in the entire universe, and also why helium got so expensive. All right, so here is something about particle interactions. In this little graphic, we see, first we saw a muon going through the detector. On the middle is a silicon camera, and in the intermediate layers, there are layers of detectors that detect electromagnetic radiation, the hadronic particles, as well as the muons that went through the steel and go through the chambers that we saw outside. Each particle, when it interacts with each detector, leaves a different signature. There are about 100 million channels in this detector that collect the signals from each detector where a particle went through. And when you reconstruct all of these hits of all of these particles that went through in a collision, you reconstruct what we call an event. The detectors are very giant. This is the other detector. I showed you Atlas before. This is the CMS detector. And the CMS detector, unlike the Atlas one, was built on the surface, and then it was brought down. And it was built in 12 different pieces, like a Lego. The heaviest of these was a 5,000 piece, which had the magnet. And in our case, CMS means compact muon solenoid. The magnet was a solenoidal magnet. All right, so this is the day after the first collisions in September 2008. The first collisions were September 12, and September 18, we blew it up, as you remember. And the Lynn Evans is on the right, and I am on the left, and my hair is unwashed, and his hair is uncombed, and we're talking about the success of the machine, also being worried about when we are going to have collisions in the detector. Then we blew it, we fixed it, and there we are in December of the next year. I was running the first shift where we took data at the highest energy. We beat the energy of the Tevatron. This was 2.6 TeV. And now the difference is that and despite the fact that I was on night shift, you see I'm dressed well, I have my hair is washed, so you can imagine what happened. My mom and dad were there, and in the middle of the night, we woke up the spokesperson, Jim Verdi, in order to make a record of the fact that we were the first to take the highest energy collision. So we were very excited. Now, the particle discoveries within the time of the LHC, I want to show you that in 9 months of the LHC, we have rediscovered all the particles of the Standard Model from a century. So the machine, the first thing that you do when you bring a new machine up is you try to verify everything that you know so far and that it is correct. And so we have done that in a very fast period of time from 9 months running and a few months of cosmic ray data. And we had a visit, of course, from Peter Higgs, because the LHC was built to discover the Higgs. That was the main mission of the experiments. Both ATLAS and CMS were designed, each of the elements of the detector was designed such that we are able to identify a Higgs in a mass range that it is very huge, from 100 GeV all the way to a TeV and more. It is important to keep in mind that the Higgs is, the hunt for the Higgs is not just at the LHC, that we had decades. In fact, the largest time for the hunt of the Higgs was at experiments before at the Tevatron, at Fermilab in Batavia, Illinois, and before that back in Geneva at the LEP. And experiment by experiment and data period by data period, we narrowed the window. All these stripes that you see, the colored stripes, the vertical colored stripes, are exclusion regions where the Higgs is not. And there was this little slither that was left here that was allowed for the Higgs. And look where it is between 122 and 126. And this came in 2011 when we had the first LHC run. So I want to put a little bit of emphasis on the data, because we are, the LHC, this is in fact a picture from the Department of Defense. The internet before the LHC around 2008 is one little dot, one pixel in this superhighway of data, according to the DOE, and it's true in terms of data transfers, of networking, of distribution of data, the grid, and between 2008 and now, we have learned from building the computing system of the LHC, we have learned a lot. The thing to remember here is that we are susceptible to between 100 terabytes per second to 1 petabyte per second of data. This is a lot of data. It's no comparison to the data that Google is handling. And so, of course, with the advent of all the social media, there is now data everywhere of that sort of magnitude. On the right is a little graphic that shows you the data of the LHC compared with the tweets per year in 2011, the human memory, the World of Warcraft servers, the US Library of Congress, and Wikipedia, where Wikipedia is a dot, and the Large Hadron Collider is over there with the 25 petabytes per year. This is how the network is looking right now due to the LHC. It's becoming a live organism of hardware and software in communications. It's extremely important. I just want to note on the bottom right there, for those who can see it, that we actually saw by monitoring all the networks, because we have to, since we cannot keep our data on site and we have to distribute it and we monitor our networks, we saw when Syria, for example, lost their internet a couple of years ago. In the future for the LHC, what we are targeting is, in principle, real-time, alive, adapting networks that are intelligent and self-organizing in order to deal with an increase of 1,000 and another 1,000 and another 1,000 of data. So we're talking about from petabytes going to zettabytes and yoctobytes. This is huge increase in data that we have to deal with, and we have to deal with not only talking about big data, but in fact talking about smart data as well. So here's the eureka moment at the LHC. Well, the eureka moment was we made the announcement on July 4. We described all the analysis in a publication that it is available to everyone. One publication from Atlas, one publication from CMS. We had the 3 channels that gave us the discovery described in there, and the channels or the final states or the Higgs decays that we detected that gave us the Higgs was in 2 photons, 2 Z bosons, 2 W bosons, all bosons. This is why on the first slide I said the issue of the electroweak symmetry breaking is settled for what has to do with with the bosons. You see on the left there is the congratulatory note from Peter Higgs, who said, "Thank you for my Nobel Prize." And on the right side, we see the note that we got, all the experiments. This is the note for the US CMS. You see the note that we got from Holdren, from the Office of Science, who acknowledged that the US has played an invaluable role in the discovery of the LHC in terms of not only funding and people, but in terms of all the know-how, technology that was built in this country in the past 50 years. Okay, so now we're going to see how the signal looks like. And we're going to see it in what is called the golden mode first. I want everybody to be noting, as we accumulate data, I want you to be looking at the data, and I want you to be looking at the blue histogram. The blue histogram is what I would expect from the standard model without the Higgs. Don't look at the red histogram at the moment. Look only the blue and the data. If you look at this by eye, this is why it's called golden mode, you see an excess of events at around 125 GeV. This is the Higgs. This is the Higgs decaying into 2 Z bosons. Each of the Z bosons decays into 2 muons. So you've got 4 muons in the final state, or 4 electrons in the final state, or 2 muons and 2 electrons. You analyze these and you get the mass of the Higgs. The histogram there is if you do the theory, the simulation of the theory for a Higgs of 125 GeV, so that you can compare your discovery with some theory, and the theory you compared it there, the red, is the Higgs. In the other channel, which is not so golden, and you will see why, it's a little more difficult, it's the channel with the 2 photons, and note there, as we accumulate data, there is a little blip, which in the data minus the fit, it appears also like a little blip. This is the discovery of the Higgs in the 2 photon case. Much more difficult because the background you see, the background is the blue, is very huge noise compared to the signal. So let's look at some event displays. The event display from the 2 photons. This is real events. The little dots and the little tracks that you see around is from reconstructing all the particles of the event in the tracker or in the calorimeter. And the 2 towers, on the 2 orange towers that we have on the one side and on the other side, is representing the photons. The photons are dotted because they don't leave, they're not charged particles, so they don't leave any signals in the tracker. If we look at the ones, how they look with 4 electrons or 4 muons, okay, we're going to go a little now weird here, but you see 4 tracks on the left. These are the muons. Now on the right, 4 tracks and electromagnetic energy. These are the electrons. So the electrons look like little towers. They have little towers like the photons, and also they have tracks. And this is, in words, this is how we actually do the reconstruction of particles. We go through all the detectors and we figure out which particle leaves which characteristic signature in which detector, and we reconstruct everything together. Okay, so now I want you to take a breath, because what I'm going to say maybe you have never heard. But the Higgs, it doesn't come really from particle physics notions. On the contrary, it comes from notions, it's not on the contrary, I would say in parallel. It came from notions about materials. So when people are studying materials, ferromagnets, and when ferromagnets become magnets and when they are not magnetized, and why this is happening with changing the temperature, people started understanding that there are phenomena of symmetry breaking in materials. And materials are easier to study because they are materials. You have them, you study them, you can put pressure on them, you can put the temperature on them, you can measure thermoelectrics, you study them. So this was emphasized specifically for what has to do with symmetry breaking by Nambu, our professor from the University of Chicago who got the Nobel Prize for spontaneous symmetry breaking. And he talked in his Nobel lecture not about he talked about cross-fertilization, a case of cross-fertilization, meaning cross-fertilization between condensed matter and particle physics. I should say when I showed you the stamp that the language that I talked about, quantum field theory, with the diagrams and all that, refers to particle physics and condensed matter, quasi-particles, etc. So the language already is shared, but also the phenomena, and the description of the phenomena, despite the fact that they are at different scales, which is mind-boggling, okay? And then the analogy is not exact, we have to keep in mind. So for physical systems like ferromagnet, a broken symmetry is giving rise to what we call spin waves. Which is the symmetry? The symmetry is rotational invariance. It has to do with the spin and how they are aligned in the ferromagnet. In crystals, if you break the symmetry, which is translational symmetry, you put in crystals, and you put all the atoms, and they have a lattice. If you break the symmetry, the translational and rotational symmetry, you get something which is called phonons. And in superconductors, you break some more esoteric symmetry, which is a gauge symmetry of the particle number symmetry, and you get Cooper pairs. And so these kind of notions of symmetry breakings that give you states, they were not particles, spin waves are spin waves, but Brian explained to you waves and particles and states are all states in the end in the bigger language. And so you apply these notions from condensed matter ideas to particle physics, and the difference is that you don't have a material, you have the quantum vacuum. So now the analogy is that the quantum vacuum is not is almost a representation of many quantum states. It's not a representation of something pure and one. And this is also the magic of quantum mechanics. Now, Phil Anderson, this is again the Mexican hat potential, where the states that they are on the trough, which are the red, are the Higgs modes, and the states that are around the circle are the W's and the Z's, and they're called phase modes. Phil Anderson pointed out that the quantum vacuum is like a many-body system in the same sense as in the condensed matter systems, and he wrote this paper, which was called More is Different in 1972, talking about symmetry breaking as a property of large systems. So while we're talking about elementary and going deep to elementary, we have to keep in mind that there is interactions, and the universe is not made by one particle not interacting with anything. And in all of what we are talking about, there is also complexity. In fact, after symmetry breaking, all the particles get mass, and you've got some sort of complexity there. And in fact, in condensed matter physics, for the past many years, people are tweezing out Higgs states from condensed matter systems. From Bose-Einstein condensates, in superconductors, and the energy scales are much different. They are little tiny Higgses in terms of EVs you see there. There are 13 orders of magnitude in the case of Bose-Einstein condensates compared to let's say, the cosmic Higgs, which is the elementary Higgs, the spontaneous symmetry breaking in the vacuum Higgs. And in fact, I met somebody very recently from a lab in Max Planck, where with a set of rubidium atoms, they make a lattice, and they start bombarding it with 3 lasers until they go into a phase transition between superfluid and insulator of this material. And in exactly where the phase transition is, they get a Higgs, and the Higgs is there in the data. Now the Higgs is not measured in MEVs or EVs because it's practically 0. It's 400 hertz, which is very small. If you consider 1 terahertz is about 1 EV. So Higgs, there are tons of Higgses in condensed matter physics. They are different, but the symmetry breaking, the considerations are very, very similar. So let me turn now from the history. Let me turn to the SUSY partners, but I want to say that why I'm going now from the Higgs to SUSY. There is a big anathema with the Higgs, that in quantum field theory, the Higgs corrections quantum corrections can be bigger than the Higgs. And this is like your lunch being bigger than you. So this is not very normal. So SUSY came in for other reasons, to explain fermions, in fact. But SUSY comes in and it fixes that problem. So you can say that the electron in superspace, and again, Robert will explain to you what is this new quantum coordinate, where you don't have just space-time, but a new angle, a new quantum coordinate. You can write it as the super electron, which is a partner with spin 0, and the electron, the normal electron. So a linear combination of these is the bigger field. Now, this supersymmetry with the assumption that the particles, that supersymmetric particles, will be at the TeV scale. This is a necessary assumption. Is the most complete and beautiful framework in order to complete the standard model. Now, the attractive property is the property that I told you, is that it helps us with the Higgs pathology, but also, as a matter of principle, it's not just an ad hoc inclusion of new particles. There is a symmetry being involved. This is how the SUSY partners would look. If we had the standard model particles, the Higgs is added there, and now we have all the superparticles. So we just doubled the particle spectrum that we have. And again, somebody might ask, why? This sounds very complicated. Why do you double all the particles that you have? And there is an added value to that, however. The supersymmetry gives you out, as a theory, more than assumptions you put in. And this is why we have been fascinated with this theory for the past 40 years, 40-something years. And this is why we're not giving it up. And also, possibly in the next 2 years, we are going to actually discover a kind of supersymmetry. Not the vanilla kind, but a kind of supersymmetry. I'm not going to go through that because Robert is going to explain it to you. This is the language in diagrams of how the pathological diagram with the big quantum corrections is being fixed by adding these twiddle particles, the superparticles, with opposite spin. Mathematically, if you add all these diagrams, there is a cancellation, what we call a cancellation of the divergences. So the SUSY models have also many, many other features. I'm not going to go through the features, but I'm going to tell you one of them, which is spectacular, and it was not put in the theory. The SUSY models are giving you a particle that could be the entire mass dark matter of the universe. So the big question that we have for what is dark matter could come to be solved by the supersymmetric particles. And this is why, in a visual term, if we look at this event over here, you can see yourselves that there is a transverse view of a detector. It's pretty symmetrical in terms of the detector itself, and it is completely asymmetrical with where the energy deposits are. So we've got one half of the circle filled with energy, and the other half, there is nothing. This type of events with imbalance in the event could be the story behind what we call a neutralino. It's not a neutrino, it's a neutralino that has escaped detection from the detector, and that could be the dark matter particle. I have to go fast now, but my prediction is that if the supersymmetry is the solution to the problem with the Higgs, the so-called naturalness problem that we talk about, then we are going to see it in 2 years from now. And it's going to be 1.4, 1.5 TeV partner of the gluon gluino. And we have had cases like that where we were just around the corner with LEP and we missed the Higgs like that. So now I'm going to go 5 or 10 minutes over time, no more, because I want to tell you the big beyond the Higgs. First of all, within the Higgs that we found, we have not clarified completely that it is the standard model Higgs. We have not measured completely its characteristics. We're doing this now with the full data set, and we will do it as we go in the higher energy run, which is going to be the almost 14 TeV run that will start in a year from now. We have to clarify if there is more than one Higgs and how many more. And the reason for that, I alluded when I was talking about all these flavor problems, that we might have to have an extended Higgs sector to understand all these different patterns in the masses of all the particles. And this is, in fact, one of the biggest part of the LHC challenge and program in the next run. Supersymmetry, in fact, predicts, when I talk about the extended Higgs, the richer Higgs, supersymmetry predicts 5 Higgses, that they are different in masses and other properties. Okay. Now, you might have read that, Eureka, the Higgs, let's celebrate champagne and go home. No, not the way it is. We are scratching our heads completely with the mass of the Higgs we measured, because in fact, the mass of the Higgs, it's giving us a borderline disorder. The 126 Higgs mass is at the edge of the stability of the vacuum, and I will explain that in a minute. It has to do with a calculation for the vacuum of the universe based on the mass of the Higgs and the mass of the top. And the 126 is giving us a big headache if there is no other new physics. I will explain in a minute. If we start thinking about supersymmetry the way we have been thinking about it for 40 years, the 126 is giving us a very big headache. It is at the border of being acceptable for normal SUSY, which is the minimal supersymmetric standard model, MSSM. And you see the border there, and in order to accommodate it, mostly we have to make extensions of supersymmetry. So supersymmetry, the vanilla supersymmetry, is not good enough for this 126 Higgs. And if we consider other stronger dynamics and composite Higgs, it is rather too low. So it's too fat to be MSSM, it's too low to be composite. If there is no other physics, it makes a disaster for the vacuum of the universe. So this is kind of a situation where after the champagne, you have a hangover and you wake up to this problem, and you need now to go and analyze the data. Now, the question is, for the connections of the Higgs to the beyond, is it indeed true that, is it indeed the case that the Higgs destabilizes the vacuum? How does the scale, in other words, why the Higgs has the 126 GeV mass, and then the connection of the Higgs to the dark matter. Now, I think that I alluded again in the flavor problem is that we need to understand how the Higgs talks to the neutrinos, and if it is also related to inflation or dark energy. All of these connections are really open-ended. These are questions. These need a program, an experimental program, both a precision program and a discovery program. Now let me show you the stability. Let's not read the words, but let's see the plot there. This is the little part of the pant of the Higgs Mexican hat, the pant that it is on the bottom of a bottle. And as I will change it, you see that when the trough was very well lined up, but then as I change the potential, I can make it turn around, so the Mexican hat can go around. So what I thought was a stable state could actually be a state like on the bottom right plot, where I can tunnel from a false vacuum to a true vacuum because my Mexican hat potential turned around. So now, in fact, the opposite can happen as well. But in this case, I'm saying that if I go from the false vacuum to a better energetically favored vacuum, the universe would bubble away and it will appear in a different vacuum. Of course, this sounds, it would be 10 to the 100 years, and this sounds like big nonsense. But in fact, if I consider no other physics, this is what I'm led to with the quantum mechanics that I know. And of course, this is something that we need to investigate. If I put supersymmetry, of course, this is in the plot that is showing here. The metastability is shown in yellow, and it is given as a function of the mass of the Higgs and the mass of the top. Of course, if I put the new symmetry, supersymmetry, and new particles, this plot on the left goes away, and I have no problem with the universe or the vacuum. I'm not going to bubble away. So I'm going to now talk, the last section is about matters, the dark matter, and how it is connected also with the Higgs. So, well, that's luminous matter. We see it from all the observations in the sky, and this is dark matter. We don't see it. It's also not exactly transparent, but if I put dark matter in front of luminous matter, I will see distortions of luminous matter as if the dark matter is a lens. Dark matter interacts gravitationally. The first dark matter, let's say, discovery, I would say, of the dark matter was by Theodor Zwicky, who was a Hungarian physicist at Caltech, and he was really nasty, and nobody liked him. And therefore, when he published the paper that in a cluster of galaxies, they were not galaxies then, they were called nebulae. In a cluster of galaxies, he calculated with a virial theorem from the gas how much mass that would have. And that's, the virial theorem is talking about potential energy and kinetic energy. And he found a factor of 500 more than the calculation with the luminous matter. So he wrote a paper, and this is the paper, and nobody believed him because he was so nasty, not because they didn't want to consider him, to consider his findings. Now, that was the dynamics of many galaxies, the clusters of galaxies. For the galaxies themselves, how galaxies are being comprised, they're being comprised by stars and gas and dust, the black hole in the middle, huge black hole in the middle, and also dark matter. And this was inferred by measurements of the stars, we call them the rotation curves of the stars in the galaxy, and the rotational curve is on the y-axis, and the r, as far as we go from the middle of the galaxy outside, is on the y-axis. And just with Newtonian mechanics, you would expect that the rotation curves would slow down as you go out of the galaxy. In fact, the data is observed to be flattening there. And so came the whole headache about what it is that the baryonic matter in the stars, in the galaxies, is scaffolding to, so that you get this stabilization there. And the thing that first people did is they assumed that the galaxies are embedded, the galaxies are flat, and they're embedded in a big dark matter halo, and we didn't know what dark matter is, but we knew that from this that it interacts gravitationally. For the astronomers, that's pretty much the end of the story, because they don't care what it is. So the discovery is done, there is dark matter, we've got it, here it is. Vera Rubin was the first one to do these rotation curves. And again, this is showing the same diagram and the Keplerian expectation. And this is showing the actual data that she measured. So there's another way that you can see it, that you can observe it in the sky that there is dark matter, and this is with lensing. This will be explained in the last lecture a little more, but gravity, if you put a big gravity, a big mass gravity, the light from a faraway star system, galaxies and clusters of galaxies will be distorted as if you go in the distortion mirrors. So you will see in the sky images that have little lines around them of galaxies like this one. And this is a simulation of which kind of distribution the dark matter would have in order to get this type of distortions. The distortions are these little lines that you see, which are showing you that there is what we call gravitational lensing. Now, the best, how is this, why am I talking to you about the skies and dark matter and astrophysical observations? The best clue we got for what dark matter is the particle, a kind of particle like the particle that is the SUSY, the supersymmetric, lightest supersymmetric particle, which is a very weird thing because supersymmetry was not built in order to have this particle in. On the left here, it shows you the mass energy budget of the universe, and we are the special little tiny percentage of the two slices. One is the neutrino slice, and one is the rest of all the baryonic matter. And the rest is dark matter, 23%, and 73 dark energy, for which when you don't know what it is, don't even speak of it, but we do anyways, and look how much we speak about it. In the past 5 years, we have gotten a renaissance of theories of dark matter because we haven't found which particle it is. We have been looking for it as a particle with experiments in the sky, experiments underground, and the collider experiments, and we haven't found it yet. And so to understand which space is there still to explore, we have made tons of theories of dark matter: warm dark matter, axion dark matter, soliton dark matter, sugra, gravitino, cube balls, all sorts, sterile neutrinos, all sorts of different kinds of particles and all sorts of extensions of the standard model. So the dark matter interaction with matter, what we know is via gravity. And this is the famous bullet cluster. You will get a good explanation about it. But in this case, the dark matter does nothing when galaxies collide, and the normal matter, dust and gas, they scatter. Could it be, however, that dark matter interacts with normal matter with the weak interactions, for example, with the Z? It could, but we excluded it. We have experimental data that we excluded it. Could it be that it is actually interacting with normal matter through the Higgs? Yes, it could, and we haven't excluded it. And we're very close to getting there on all the experiments underground and the experiments and the collider experiments. Could it be that there is something else? Of course, always there's something else that it could be. But right now, it's the time to actually, we have cornered ourselves in a situation that we will have enough experimental data to actually speak definitively about dark matter, even better to discover it. I'm not going to go through this slide except to say that there is a miracle there. And the miracle is the coincidence. The coincidence, you can say, that the neutralino, the lightest supersymmetric particle, fits the bill to cover the dark matter of the universe, the relic abundance for the dark matter of the universe. Here is in plots the words that I told you, that we are almost there. Here, the experiments are the experiments of the future that will explore dark matter interaction with normal matter. These experiments have not been done, and these experiments up to here have been done, and this is where it would be if it was via the Higgs. So we are going down here, and we will know very soon from these experiments whether the area where the Higgs is the way the dark matter speaks to matter is, and so this is extremely important time. There are all sorts of dark matter evidences. You hear it in the news. Nothing is definitive. There are many anomalies. Nothing is definitive. And this is a totally open-ended puzzle. And I think Dark matter and new physics is the biggest, absolutely the biggest problem in physics today. This is a network that represents the dark matter in the universe, and it looks like indeed the scaffolding where matter, the luminous matter, is hanging on to. It's gravitational for the moment, and we don't know anything else other than that. This is the last slide. I want to emphasize for the Higgs connection to the beyond, the major, important, big topics are the dark matter, whether the Higgs is a portal to the dark matter, is the electroweak baryogenesis, and you're going to hear a little bit about that, and the electroweak phase transition. This is the first real cosmic event in the evolution of the universe where we actually have the phase transition and we have mass endowed to the particles. And also the principle that creates and stabilizes the electroweak scale, how the Higgs talks to the neutrinos specifically with their little masses, and the dynamical origins. Do we have more Higgses? The dynamical origins of all the flavor, and the masses, the mixings, and CP violation. And of course, when we solve all of the above, extra credit comes if we figure out what is the connection of the Higgs with dark energy. Namely, this is going to be covered in the cosmology lecture about the acceleration, the expansion of the universe at an acceleration. So this needs a multi-decade global experimental effort on many fronts: particle physics, nuclear physics, astrophysics, even precision astronomy can give input, and of course cosmology. I have told you this. I have made the prediction that we will find that we can find supersymmetry at the LHC. So so far we haven't, and if we don't on the next run, you will hear me being at a pause because I think we need to have new ideas. If we don't find super partners at the next run at the energy scales that we expect them, then we're going to be looking for new ideas in this field. That's the end. Thank you.